Hello, everyone. Welcome to this webinar as part of our 2021 Analytical Extravaganza. I'm Brian Field, LCMS Sales Specialist for the Pacific Northwest, Rocky Mountain States, and Alaska at Shimadzu Scientific Instruments, and I'll be your moderator today. We will hear from Dr. David Erickson, the Director of the Endocrine Technologies Core at Oregon Health and Science University, about the analysis of steroid hormones by MSMS and advancing researches in HIV/AIDS and reproductive health. Before we start, I wanted to share a couple of notes for our viewers. This webinar console has a variety of items to help enhance your experience and interaction with us. In the screen, you'll see the following items. The slides will appear on the left-hand side. Directly under the slides, you will see a resource list with clickable links relevant to the material being presented today. On the top middle is the widget for questions and answers. Please submit your questions during the presentation through this widget, and we will answer them during the Q&A session. Just below the Q&A box are the moderator and speaker bios. You may expand the items here to learn more about us. On the right are survey questions that you may fill out anytime during or after the presentation. Finally, at the bottom pane are the icons to bring up all these widgets in case they are minimized or hidden. Again, if you are just joining us, I'm Brian Field, your moderator, and today we will be hearing from Dr. David Erickson on the topic of analysis of steroid hormones by MSMS, advancing research in HIV/AIDS and reproductive health. All right, without further ado, let's get started. Dr. David Erickson is the Director of the Endocrine Technologies Core at Oregon National Primate Research Center. The Core provides essential endocrine assay services and specialized expertise to investigators in order to advance a wide array of research in a number of species, with a focus on non-human primates. The Core supports investigators with varied research interests, including reproductive health, nervous system diseases, obesity, and HIV/AIDS. Dr. Erickson has recently published articles in journals such as Contraception, AIDS, and Nature Communications. He earned his PhD from Penn State University and completed his postdoctoral training at Texas A&M University and University of California, San Francisco. Dr. Erickson was a research specialist at UCSF before taking his current position as ETC Director at ONPCR. And now I will hand it over to Dr. David Erickson.
I'd like to thank the folks at Shimadzu for inviting me to give this talk. I'd also like to thank all of you for attending today. This presentation will cover my lab's work in supporting research in HIV and AIDS and reproductive health through analysis of steroid hormones by MSMS. The first part of the talk will cover the methods used in my lab, and then I'll move on to discuss application of these methods to two research projects. Oregon National Primate Research Center was established in 1962 and is currently one of 7 federally funded national primate research centers in the U.S. We have been affiliated with Oregon Health and Science University since 1998. There are 6 research divisions at OMPRC investigating such topics as obesity, diabetes, genomics, nervous system diseases, viral pathogens, and reproductive health. There's also a network of 10 research cores which supports research at OMPRC, OHSU, and outside institutions. My lab is part of this network, and we currently provide research support to investigators in each of the divisions at OMPRC, as well as researchers at OHSU and over 70 institutions both in the U.S. and around the world. My lab began as a service facility in the early 1970s and was fully incorporated as a core lab in 1979. We work with investigators researching various species with a focus on non-human primates. Our original assays included in-house extraction chromatography radioimmunoassays for steroids, but we've grown to offer over 130 unique assays on 6 platforms, including a Roche Diagnostics automatic immunoassay platform, Shimadzu LC-MSMS instrumentation, commercial ELISA and RAA, in-house RAA, Luminex technology for multiplex analysis of cytokines and chemokines, and direct iodination RAA for analysis of gonadotropins. We develop or validate a handful of new assays every year and work with roughly 75 investigators annually from academic institutions, zoos and veterinary clinics, and pharmaceutical, biotech, and translational research companies. The lab typically handles around 500 assay requests for 50,000 or more tests each year. I mentioned we have been analyzing steroid hormones since the early 1970s, but we did not acquire LC-MS instrumentation for this purpose until the early part of 2015. In April 2015, our Shimadzu Nexera LC-MS 8050 system was installed. We installed our sample preparation equipment from Biotage in June of 2015, announced the service to OMPRC in August 2015, and began analyzing investigator samples in October of that year. I was awarded an NIH S10 grant in late 2019, which allowed us to purchase a Shimadzu Nexera LC-MS 8060 that was installed in January 2020. Despite slow progress due to the COVID-19 pandemic, we were able to start analyzing samples on the 8060 in May of last year. Here are pictures of our current instruments. The 8050 is on the left and the 8060 is on the right. We've been extremely happy with them so far, and both instruments essentially run 24/7 for us to try to keep up with demand. While we do analyze more than just steroid hormones, the bulk of what we do is steroid hormone analysis, and that's what we'll be discussing today. Steroid hormones are derived from cholesterol and comprise two main classes: the corticosteroids produced by the adrenal cortex and the sex steroids produced by the gonads, and during pregnancy, the placenta. Steroids have a wide range of functions, and among others aid in metabolism, inflammation, immune function, and reproduction. There are both naturally occurring steroids and synthetic steroid hormones, both of which we'll be covering in the talk today. Aside from MS assays, two popular ways to measure steroid hormones are by automatic immunoassay and radioimmunoassay. On the top right, there's a picture of our chromatography setup for RIAs, and on the bottom right, we have a picture of our automatic immunoassay system. RIAs are excellent when properly validated, and multiple steroids can be assayed with a single aliquot. However, they are time-consuming, can lack specificity, and large sample volumes are needed for sensitive measurements. Automatic immunoassays are often used in a clinical setting and are fast, convenient, inexpensive, high throughput, and provide accurate results for patient care. These can, however, also lack specificity, and there's no ability for users to develop new assays. In recent years, MS assays have been regarded as the gold standard for steroid hormone analysis. They offer sensitivity, specificity, and automation. Large sample volumes or multiple injections are still often required to achieve adequate sensitivity, especially if analyzing multiple steroids in a sample, but the new generation of instrumentation is addressing this drawback. There is also heterogeneity in both methods and assay performance between labs. Now I'm going to move into LC-MS analysis of steroids in my lab. First, I'll go over the general approach we use and highlight alterations to this method when I discuss the specific projects. We use supported liquid extraction, or SLE, from Biotage to extract steroids from serum and plasma. For steroids, we've been using 400 microliter SLE Plus in 96-well plate format, seen in the top picture. We first mix 150 microliters of sample with 100 microliters of water containing a mix of deuterium-labeled internal standards specific to the analysis we're running. This mixture is loaded onto SLE Plus plates using a Biotage positive pressure manifold, shown in the middle picture. We incubate for 5 minutes and dilute into 2 ml glass-coated deep well plates using two 900 microliter aliquots of dichloromethane before drying down with a Biotage TurboVap, shown in the bottom picture. We rinse the collection plate with 400 microliters of DCM per well and repeat the dry down step. Finally, we carefully reconstitute the extracted steroids in 50 microliters of a methanol water mixture and transfer to 350 microliter V-bottom plates. We found the combination of the glass-coated collection plate with the rinse and extra dry down step to be critical in increasing extraction recoveries and improving our assay sensitivities. For liquid chromatography, we use the Shimadzu Nexera UHPLC system. In our setup, this includes a SIL 30A CMP autosampler, two Nexera LC30AD LC pumps, and a CTO 20AC 6-column oven. We use reversed phase chromatography on a 50 mm by 2.1 mm Restec Raptor biphenyl column with 2.7 micron particles. We sometimes use a 100 mm column to allow for additional separation if needed. Mobile phase A is 0.15 millimolar ammonium fluoride in water. This concentration was determined empirically using decreasing 0.05 millimolar increments from 0.2 millimolar. Mobile phase B is 100% methanol, and the chromatography program varies based on the specific analysis. The flow rate is typically 0.25 mL per minute and will inject anywhere from 5 to 25 microliters onto the column depending on the hormones we're quantifying. The MS analyses for the projects I'll be discussing today were performed on our Shimadzu LC-MS 8050, which is a tandem triple quadrupole system with heated electrospray ionization. For temperatures, we set the interface at 300 C. the desalivation line at 150 C, and the heat block at 500 C. We don't use the standard capillary needle in the source. We instead use a capillary B needle, which is a finer needle. The protrusion is set to 1 millimeter, which is determined empirically for each new needle we use, and also when we set up a method. Gas is supplied by a Peak Genius 1051 generator. Nebulizing gas is nitrogen at 3 liters per minute, drying gas is nitrogen at 10 liters per minute, and heating gas is air at 10 liters per minute. The MSMS conditions for each compound are optimized using the automated MRM optimization procedure and Lab Solutions software. We analyzed the data using Lab Solutions versions 5.72. Target reference ion ratios were set according to the reference ion ratio of the highest standard for each target. The default ion allowance for peak identification was 30% relative to the target ratio. We used linear regression with 1/C weighting for analysis of the calibration curves. The first application of LC-MSMS steroid analysis I'll discuss today is contraceptive hormone analysis in women. This particular study involved evaluating concordance of self-reported hormonal contraceptive use with contraceptive hormones measured in serum among a cohort of African women. This was part of a larger study to monitor the relationship between contraceptive hormone use and HIV acquisition. The ability to quantify contraceptive hormones is important to monitor adherence and efficacy of contraceptive protocols and to evaluate associations of hormone use with other health outcomes. We can also monitor interactions during drug development or develop new contraceptive protocols using existing hormones. For this particular study, we're interested in monitoring contraception protocol compliance. There have been previous studies demonstrating misreporting of contraceptive hormone use among clinical research participants. One study showed that 27% of women who self-reported no contraceptive use had detectable hormonal contraceptives in their blood. This demonstrates a need for objective measures of contraceptive hormone use. There is a relationship between hormonal contraceptive use and the acquisition of HIV and other sexually transmitted infections, namely an increase in infections in women using depo-medroxyprogesterone acetate, also known as Depo-Provera. Misclassifying women with respect to contraceptive use could bias results in epidemiological studies. At the time we performed these analyses, there were few methods for determining multiple progestins in a sample, and even fewer methods allowing for simultaneous measurement of progestins with estrogens or endogenous steroid hormones. The objective of this study was to develop such a method and investigate the degree of misreported hormonal contraceptive use in a cohort of HIV-infected and uninfected African women to ultimately further investigate the relationship between hormonal contraceptive use and HIV infection. The method we developed was for the simultaneous quantification of estradiol, progesterone, ethanoestradiol, etanogestrel, levonorgestrel, medroxyprogesterone acetate, and norethindrone in serum samples. To accomplish these analyses, we used the approach for steroid hormone analysis I went over earlier. This slide shows some of the parameters specific to this method. In the top image, we have the MS parameters for the 14 items we measured, including 7 target hormones and 7 internal standards. The picture on the bottom left shows our LC program, which started at about 60% B, increased to roughly 90% B, and then returned to baseline for re-equilibration before the next injection. The bottom right image is a screen grab of the scheduled MRMs for the 7 target hormones and 7 internal standards. The total runtime is approximately 8 minutes per sample or injection, with all of the hormones and internal standards analyzed in roughly 3.5 minutes. This is an MS chromatogram of the method, showing good separation of target hormones and internal standards while maintaining excellent peak shape. There were some matrix effects apparent with the deuterated standards as evidenced by the slightly different retention times between standards and targets, but this did not affect accuracy or precision. The calibration curves were linear throughout the assay range, which ranged from 10 to 40 picograms per mil on the low end of the curve, depending on the target, to 10 nanograms per mil on the upper end of the curve for all targets. This slide compiles relevant assay characteristics over 14 sets of analyses. The asterisks indicate that the value was adjusted to account for estradiol and progesterone present in normal serum. Accuracies range from 95 to 108%, and imprecision as measured by the coefficient of variation ranged from 4 to 12%. Lower limits of quantification were 10 picograms per mil for estradiol, ethanoestradiol, and progesterone, 20 picograms per mil for etanogestrel, levonorgestrel, and medroxyprogesterone acetate, and 40 picograms per mil for norethindrone. Because of the low noise found in most modern MSMS instruments, we did not use the traditional approach of signal-to-noise ratio to evaluate each assay LLOQ or limit of detection. Instead, the limits of quantification were determined to be the lowest and highest concentration on the calibration curve with accuracies of 80 to 120% and CV less than 20%. Instead of an LOD, we established a method detection limit, or MDL, for each assay in the method. The MDL is defined as the minimum concentration of an analyte that can be measured and reported with 99% confidence that the analyte concentration is greater than 0. These ranged from 3 to 7 picograms per mil in this method. Extraction efficiencies were greatly improved with the inclusion of glass-coated collection plates and the additional DCM wash. We ran 2 sets of control or test samples. The first is a set of controlled clinical samples, and the second is a set of pooled samples from the African cohorts. The clinical samples demonstrated specificity of the method. We saw no evidence of exogenous hormones in the controls, only MPA in the group administered injectable contraceptives, LNG and ENG in the implant users, and EE2 and LNG in the oral contraceptive users. These results show that the hormones quantified are all expected for each group. Analysis of the pooled cohort samples demonstrated that we had excellent accuracy with acceptable CVs for all of the assays. We did not have sufficient sample numbers or concentrations of EE2 in cohort samples to produce an adequate sized pool for testing in this manner, which is why there's no data for EE2 in this table. We applied this method to samples collected as part of the Partners in Prevention HSV/HIV Transmission Study, Couples Observation Study, and Partners PrEP Study. The objective of these projects is to investigate the possible increase in HIV acquisition and transmission in women using various contraceptive hormones. We analyzed 1,102 samples from 664 heterosexual women in 7 African countries. These samples were taken at monthly or quarterly visits. These are the results of the analysis broken up by contraceptive method: no contraception, injectable, oral, and implant. These are quantifiable hormones versus what was self-reported by women in the cohort. We see evidence of all hormones across women who are self-reported non-users. Evidence of oral contraceptives in women who are self-reported injectable users. Evidence of injectables in women who are self-reported oral contraceptive users. And evidence of injectables in women who are self-reported implant users. In all groups, we found evidence of discordant hormonal contraceptive use after LC-MS analysis. Breaking this down further, we see that about 80% of women using injectables had only the expected hormones in their samples, while this number was 27% for oral contraceptive users and about 90% for implant users. Roughly 14% of women who self-reported no contraceptive use had evidence of contraceptive hormone in their sample. 62% of oral contraceptive users had no evidence of hormones in their samples, but this could be affected by sampling during a placebo week. Admittedly, we did not have control over the timing of sample collection, so that is a variable we have to consider for this number. To quickly summarize the previous slide, 82% of the LC-MS results matched self-reported use. Depending on the contraceptive method, between 8 and 62% of self-reported users had no evidence of the reported method, which breaks down to 62% in oral contraceptive users, 17% in injectable users, and 8% in implant users. Unexpected hormones detected in 2 to 11% of samples, 11% in oral users, and 2% in implant and injectable users. Among self-reported non-users, 14% had one exogenous hormone present, and there were no differences in proportion of misreporting by HIV status. To sum up this part of the talk, we developed a sensitive, selective, specific, precise, and accurate LC-MS method for simultaneous quantification of 5 exogenous contraceptive hormones and 2 endogenous steroid hormones using small sample volumes and a simple sample preparation procedure. The reliance on self-reported contraceptive hormone use will involve misreporting and inaccuracy in exposure classification for epidemiological studies. An objective analytical method to ensure that study populations are accurately categorized is necessary. For the final part of the talk, I'm going to switch gears a bit and talk about monkeys and a reproductive health model that has been under study at OMPRC. We analyzed steroid hormones in samples collected from a non-human primate model of chronically elevated androgen and a Western-style diet, which is designed to mimic polycystic ovary syndrome, or PCOS. PCOS is an infertility disorder affecting approximately 5 to 15% of women. According to the Rotterdam criteria, 2 of the following must be present for diagnosis of PCOS: oligomenorrhea, or infrequent menstrual cycles, hyperandrogenemia, or increased androgen production, and/or polycystic ovaries upon ultrasound. There is a fourth criterion that is not required for diagnosis of PCOS, but is commonly found in women with PCOS, and that is obesity and insulin resistance. One of the criteria for PCOS diagnosis is hyperandrogenemia. The monkey model developed at OMPRC features induced hyperandrogenemia using testosterone implants at menarche, or the onset of menstrual cycles. The goal was to approximate 3 to 4 times the androgen levels seen in control animals. The testosterone treatment was combined with either a Western-style diet containing 36% fat or a control diet with 12% fat. After 3 years of treatment with testosterone and a Western-style diet, these monkeys exhibit impacted decidualization during implantation for pregnancy, a PCO-like ovarian morphology, weight gain, fat mass gain, and mild insulin resistance. I would like to note that this is not a true model of PCOS because it does not feature the increased luteinizing hormone pulsatility found in PCOS, but for the purposes of this talk, I'm going to refer to it as PCOS. As for the impact of the hyperandrogenism associated with PCOS, it may contribute to higher rates of pregnancy complications, a greater risk of preterm birth, gestational diabetes, or cardiovascular complications. Hyperandrogenemia is not required for diagnosis of PCOS as mentioned earlier, but steroid hormone profiling is needed to better understand the complicated pathophysiology of PCOS. Earlier, we discussed a few hurdles to steroid analysis by LCMS, and there are a few additional considerations when working with non-human primate models. In general, steroids are often found in low concentrations in circulation, sometimes in picogram per ml quantities in blood. Steroids also exhibit poor ionization efficiency due to a lack of polarity, which can be a challenge during MS analysis. In monkeys, we also have sample volume to consider, because we have to follow what's known as the 10% of 10% rule. That is, if 10% of a monkey's body weight is blood volume, equaling roughly 100 milliliters per kilogram, we can draw 10% of this volume. This is considered over some period of time, usually over 2 to 4 weeks. This means that for female rhesus macaques that weigh 5.5 kilograms, we can draw 2 mils of blood per day or get 1 mil of serum per day. There are also limitations specific to how things operate at OMPRC. Investigators often draw blood daily for menstrual cycle monitoring, which my lab also performs, and then the remainder of these samples are used for additional measurements, which can limit sample volume to about 250 microliters for LC-MS or any other number of assays. Given that information, our objective for this study was to develop a robust and sensitive method for simultaneous analysis of 7 steroid hormones of different classes, glucocorticoids, estrogens, progestogens, and androgens, and use this method to analyze serum and follicular fluid samples collected from PCOS monkeys. The method we're going to go over now features the simultaneous quantification of cortisol, cortisone, testosterone, estradiol, estrone, progesterone, and androstenedione. So again, just a few project-specific changes from our standard method. In this case, we use Strata DE SLE plates from Phenomenex instead of Biotage SLE+. For extraction of serum samples, we combined 150 microliters of standard QC or serum sample with 200 microliters of water containing the internal standard mix. We then eluted with 3 600 microliter aliquots of DCM and dried down under forced air before reconstituting and analyzing by LC-MS. Follicular fluid was a little more challenging. Available volumes are much smaller, and we also needed to split these samples for other analyses. We ended up combining 10 microliters of follicular fluid with 200 microliters of water and internal standard mixture, and proceeding through the rest of the extraction procedure as described with the serum samples. The calibration curve was an 8-point curve ranging from 20 picograms per mil to 80 nanograms per mil. We analyzed these samples on our LC-MS 8050. The chromatography setup was the same, using the same biphenyl column from ResTech and the same mobile phase setup as described earlier. The flow rate was again 0.25 mils per minute, and we ran mobile phase B from 65% up to 100% over roughly 3 minutes, and returned to 65% until 10.5 minutes for re-equilibration. The targets eluted over a 3-minute period. Here's a chromatogram showing separation of all 7 target hormones and 7 internal standards. The peaks on the bottom are magnification of peaks 3 through 6, cortisone, estradiol, and their internal standards. Like the previous method, we saw good separation of target hormones and internal standards while maintaining excellent peak shape. This table compiles the assay parameters for each target hormone. The LLOQs, as measured by the amount of hormone on the column, ranged from 0.49 picograms to 7.8 picograms, which translated to 6.5 picograms per mil to 104 picograms per mil when volume was considered. Accuracies and CVs were all within acceptable range. The upper limit of quantification for each assay was about 27 nanograms per mil, and all calibration curves were linear throughout the assay range. The animals used in this study were female rhesus macaques near the onset of menarche, or approximately 2.5 years of age. They were implanted with silastic capsules containing either cholesterol for the control or testosterone, and this was combined with either a standard diet or Western-style diet with higher fat content. This table shows a breakdown of the 4 treatment groups. We know from previous evaluation of these animals that the combination of testosterone and Western-style diet causes the greatest metabolic effects, namely insulin resistance. After 3.5 years of these different treatments, the monkeys were subjected to controlled ovulation cycles. We had 7 to 10 animals per treatment group. We then collected and analyzed serum and follicular fluid samples for steroid hormone concentrations by LC-MS. First, I'll review the follicular fluid results. Not much of note happening here, but what was interesting was the lack of effect of testosterone and Western-style diet on androgen concentrations in the follicular fluid. We were, of course, limited on volume, so sensitivity may be an issue with the testosterone assay, but we also did not see any significant differences in androstenedione concentrations. When we review the serum results, we again don't see much in terms of differences across the board, but we did see elevated testosterone levels in monkeys treated with testosterone, independent of diet. While we were shooting for a 3- to 4-fold increase in testosterone with treatment, we actually saw about a 6-fold increase in serum testosterone in treated monkeys. We did verify the estradiol, progesterone, and testosterone values using our clinical automatic immunoassay. So what's happening here? We didn't see the expected large increase in androgens that we see in women with PCOS. The top table shows data from follicular fluid collected during natural menstrual cycles from women with and without PCOS. Note the significant increases in both androstenedione and testosterone concentrations. The second table shows data from follicular fluid collected from women during natural menstrual cycles, the control, or undergoing ovarian stimulation. Note the large decrease in follicular fluid androgen concentrations when women underwent ovarian stimulation. The graphs at the bottom of the slide come from a study of prenatally androgenized female rhesus macaques that underwent ovarian stimulation. These data are also from follicular fluid samples. Again, note the very low concentrations of androgens in these samples, and in panel D, that there was no difference in testosterone concentrations between controls and androgenized females. What this means is that we see an effect of the ovarian stimulation process on androgen levels in follicular fluid, and that the steroid profile of serum and follicular fluid in our monkey PCOS model may be different to that of women with PCOS. To summarize this part of the talk, we developed a method for the simultaneous quantification of androstenedione, cortisol, cortisone, estradiol, estrone, progesterone, and testosterone in non-human primate samples by LC-MS. The application of the method to serum and follicular fluid of female rhesus macaques with chronic combined hyperandrogenemia and Western-style diet reveals a follicular fluid steroid profile similar to that of prenatally androgenized monkeys and women who underwent ovarian stimulation. The analysis of steroids from different classes suggests that we may have the ability to add analysis of additional steroid hormones to this method. And wrapping up, LC-MS is a powerful tool to simultaneously measure multiple steroid hormones, both endogenous and synthetic, from a single sample in a single analysis. We apply these LC-MS methods to monitor contraceptive hormone use in women participating in HIV research and to evaluate steroid hormone levels in serum and ovarian follicles of monkeys with PCOS. So briefly before we end, I just wanted to say something about where we go from here. Of course, what I presented today is just a small sampling of the projects we support in my lab. We're always trying to recruit new clients and improve and expand our LC-MS service to better support the needs of our investigator base. We recently acquired a Biotage Extrahera automated sample preparation instrument. We're currently working on optimizing the Extrahera to work with our Shimadzu LC-MS equipment and help our staff better allocate their time in the lab. We've also been working with the Shimadzu team in Columbia, Maryland on steroid analysis using the new LC-MS 8060NX. We're looking forward to the opportunity to maybe get one of these systems in our laboratory sometime in 2021. And finally, we are looking forward to integrating the RIFIX Traverse MS software into our LC-MS service. This is software that allows us to analyze LC-MS data much like we'd analyze omics data and give us the ability to analyze pathways, create heat maps, etc. We're excited about the possibility of using this to expand our steroid hormone panels to do some steroidogenesis pathway analysis. And with that, I'd like to acknowledge all the folks we've worked with on these projects. I'd like to particularly thank my staff in the ETC. Stephen was essential in getting our LC-MS service and a number of our assays up and running, and without him and his tireless efforts, we would not have been able to do what we do on this equipment. Stephen and Amy were largely responsible for producing the LC-MS data I presented today. And I'd also like to acknowledge our funding from NIH. Here's our contact info if you'd like to get in touch or have any questions. Our lab website is also there. Feel free to check it out to see what kind of other things we can do. Thank you.
Let's thank Dr. David Erickson for such an exciting presentation. Again, under the resource list, you can find more information about our analytical solutions. If you have not had a chance, please fill out the survey questions on the right-hand side to provide feedback and request additional information. We also encourage you and your colleagues to attend our upcoming webinars, which encompass a wide variety of application areas. The registration link is located at the bottom of this slide. At this time, we will begin our Q&A session. Thank you to the audience for attending and sending questions. We have time for just a few questions. Okay, here's a good one. In one of the studies, the results in the monkeys were not what was expected. How are studies typically correlated between humans and monkeys?
So that's a good question, and I don't know if we can really correlate studies between humans and monkeys. One of the reasons that rhesus macaques in particular are used for these types of studies is because their physiology is very similar to humans, but it's not exact. And so a lot of times we have to just, run an experiment, get the results, and then see what we get, and then how they compare to humans. And so I think in this case, with this PCOS study, I think the results, they aren't what we expected at first, but when we dig into the literature, we do see that they are similar to some of the conditions we see in similar human studies.
Great, thank you. We had a question come in. What type of serum-free reference do you use to build your range?
So we use serum that's as charcoal stripped as we can find. We try to get stuff that's at least twice, if not 4 times, charcoal stripped, and we still do have some issues with a few of the hormones being below the sensitivity of what the companies are able to detect in their screening, but above what we're able to detect in our mass spec. So we tend to buy charcoal stripped serum that's certified for use in mass spec, and then we just get samples of as many lots as we can and then run it through our method to see which lots look the best, and we buy as much of it as we can.
Great, thank you. There's a couple of questions about sample preparation for steroid analysis. First one, there are several derivatization methods reported in literature that discuss significantly increasing the sensitivity of analysis of some of the steroid hormones using MSMS. Are you using or have tried any derivatization methods to further increase the sensitivity of steroids for the MSMS analysis? If not, is there any reason why?
To date, we have not tried any derivatization methods, and I'm just going to assume that that's referring to the estrogens, especially estradiol. The reason why we haven't is because for most of our applications so far, we have been able to hit adequate sensitivity with the sample preparation method we're using. Most of the samples we obtain come from reproductive aged women or monkeys, and most clinicians would say that anything, any estradiol level below 20 picograms per mil for this sample population is considered low. I didn't discuss this in the talk, but we do have an 8060 MS in our lab now, And we recently were able to achieve a lower limit of quantification for estradiol of 2.5 picograms per mil using the same sample prep method that we're using here. And so there are some cases, maybe when you're dealing with juvenile samples or with postmenopausal women, you might want to get lower levels, or if you're dealing with a specific study where you need to know exact levels of estradiol, say around 1 picogram per mil or lower levels. But we have not come across a need to do that yet. Now, one last point on that subject, we are starting to deal with mouse samples, and not only do we have to deal with small volumes from mice, but also estradiol levels are usually in the single picogram per mil range in adult female mice. And so what we've been struggling with actually is recovery of estradiol through the extraction process. And so before we resort to using derivatization, we are going to start playing with, say, loading and dilution conditions on the sample prep to see if we can increase recoveries.
Great. That kind of leads into the next question. The sample preparation for steroid hormones is typically and notoriously challenging. However, you have achieved excellent recoveries and extraction efficiency for most compounds. Would you be able to discuss some tips or tricks for some of the people out there working with steroid hormones?
Sure. In the talk, I listed essentially everything that we're doing. The biggest positive impact on extraction efficiencies came when we rinsed the sides of the collection plates with the DCM after the first dry down, and when we used glass-coated collection plates. So that was, I think we're able to almost double our extraction efficiencies when we just made those two small steps. The other thing that helps with the sensitivity is obviously the instrumentation makes a big impact on it. We've been really happy with the sensitivity of the Shimatsu mass specs. And also, we're injecting roughly half of the sample into the instrument. So we're reconstituting 50 microliters of the methanol water mixture and then injecting 25 microliters into the system. And so that's really how we're able to get the combination of recovery and sensitivity is that, we're doing the extra wash and using the glass plates and then injecting as much of the sample into the system as we can.
Great, thank you. So one question about your future direction, are you considering expanding the method to include even more steroid hormones? Specifically, this person is asking about vitamin D being identified as a compound of interest in many immunological disorders.
Yeah, that's a great question. We do have plans to include other steroid hormones. I don't really know which ones they are off the top of my head right now. But vitamin D is not something that we're actively considering working on for two reasons. Number one, the assay lab at Wisconsin Primate Center already has a really good vitamin D panel. And the second reason is that all of our work is driven by investigator demand, and there just hasn't been any demand from our client base to do vitamin D analysis at this time.
Great, thank you. Okay, there's a couple more questions. We have time for a couple more. It says that ELISA is not specific, which is a common complaint of ELISA. When it comes to hormones, can you give us an example of some hormones that cross-react?
Yes, I can give you the most notorious example, and that is DHT and testosterone. And the reason for that is when you buy or use a commercial immunoassay kit, there are not separate antibodies for DHT and testosterone. So if you buy a DHT assay, you're likely measuring all of the testosterone and DHT in the assay. And so a DHT analysis requires a chromatographic separation ahead of time. And so in my lab, we've been measuring DHT by extraction chromatography, RIA, for about 30 or 40 years. And we just recently, in the last couple of months, developed a mass spec assay to simultaneously measure DHT and testosterone. So that's the most notorious example. And then there are some others. A number of the steroids on our automatic immunoassay platform have very low cross-reactivities, but they're not usually significant to affect results outside of the variation of the assay. But testosterone and DHT is the one that comes to mind.
Great, thank you. There's a couple questions about your PCOS data. This person says, I'm surprised by the result that an increase in testosterone with the Western diet creates insulin resistance so rapidly. Recently, a lot of attention has been placed on estrogen dominance, and so I would think that an estrogen excess would cause insulin resistance. Do they both? Is estrogen dominance real?
Yeah, I do not know the answer to that question. And I think the reason why is because we've been focused on looking at the androgens and weight gain in terms of the PCOS model, because those are two of the primary symptoms. One thing I did note is that this is not a true model of PCOS because it's not being caused by increased luteinizing hormone pulsatility that we see in true PCOS. So there are some aspects of the model that are not going to translate 100% to true PCOS. But that's an interesting point, and so unfortunately I can't answer that question right now, but I will look into that.
Excellent, thank you. And then one final two-part question. Other than diet, can other things be done to reduce PCOS occurrence and symptoms? And have you seen a decrease in PCOS occurrence and symptoms upon diet modification or fat reduction?
I have not personally. So the second part of the question, I have not personally seen a decrease in that. I don't think that the aim of the project here at the Primate Center is to treat the PCOS as much as it is to understand why it's happening. And from there, we can start developing treatment regimens. One of the things that's commonly done to treat endometrial or reproductive diseases like this is to use birth control pills to control hormone levels. And so one of the downsides of doing that is that women can't get pregnant. And so PCOS, I would think, is similar to endometriosis in the fact that it's more, I don't want to say it's just a lifestyle disease, but the treatments often further complicate or impact the woman's lifestyle. And so, so yeah, aside from maybe diet, losing weight, and doing those things, or using birth control is another way to treat the disease, and that, of course, has its own side effects.
Great, thank you, Dr. Erickson. I think that concludes our Q&A session. I'd really like to take a moment to thank you all for the great questions and for taking time out of your day to attend this really insightful webinar on steroid hormone analysis. For any unanswered questions, we will reach out individually to each of you whose questions we were not able to answer today. Once again, thank you all for attending and participating. We will send you an email with a link to view a recorded version of this presentation anytime. And again, we encourage you and your colleagues to attend our upcoming webinars, and the registration link is located at the bottom of this slide. Have a great day.